Section 3.2 is about compound statements and connectives. There are 4 connectors that we're going to use to connect different statements together. Remember, a statement, we reduce it down to a letter, and so they have one statement that's a P, and then we make another statement, we call it Q. For this first one, I have this upside down V shape. It means and. We call it conjunction. It's used to join 2 statements together, and when we join more than one statement together, we call it a compound statement. If I was talking about P and Q, then I would have my symbol in logic, as shown here. The other symbol that I have is a V-shaped symbol. It means or, but it's a very particular type of or. I'm going to call this the inclusive or. This is the default in math. This is called disjunction in logic. In terms of conjunction, disjunction, compound statements, negation, all these words that I'm starting to use, you don't have to worry that I'm going to give you a vocab test at any point. However, I will use these words to describe things because conjunction doesn't just mean and. It means several things. It means anything that's been joined together in a certain way. And there's tables in section 3.2 that help run you through this. So you might want to look at the table on section page 112 on table 3.4, and that would talk to you about things that this means besides and. And all of those things are wrapped up in the word conjunction. So let's talk about disjunction now. I call this the inclusive or. There's 2 types of ors that we use in the English language. Inclusive or is when I have the statement either P or Q with this idea that it includes both as a possibility, as a possible option. And this is the mathematical or. It's just a little bit different than our usual idea of or. I think our usual idea in English language is called exclusive or. In math, sometimes this is abbreviated XOR, X for exclusive. You just also see this XOR in computer programming. When the waitress says, "Do you want soup or salad with your entree?" what the waiter really means is, do you want either soup or salad, but you can't have both with your entree? That's what exclusive or means. You get the left side or the right side, but not both. Inclusive or, which is what disjunction is what we always talk about as our default setting in mathematics. You can go running today or you can lift weights. Of course, if you go to a gym, you're obviously allowed to do both. Gym memberships don't have little punch cards that say, okay, you're just on the treadmills today because you picked cardio. I think at this point there's the usual joke in mathematics where you have some sort, and by joke I mean I've actually seen this. You're at a mathematics convention, you've got some guy who's been doing mathematics for 50 years, he sits down to the restaurant because you're all going out to eat. The waitress asks, "Do you want soup or salad?" and he says yes. And then it takes like 3 minutes to convince him that she's not trying to cheat him, and the waitress that, no, we're not actually trying to be mean. This guy just has dealt with a different or than you have for the last 40 years. And they seem to never go out to restaurants except at conventions. If then is our next statement. We've got this little arrow shaped thing, and it's the conditional statement. The left side or the front part of the arrow is called an antecedent, and the right side of the arrow, what the arrow might shoot into, is called the consequence. If you think about this as a real arrow, well, if I load up an arrow in my bow and pull back on the bow and fire, that's the antecedent. And the consequence is, well, whatever I aim the arrow at gets hit by the arrow. And that comes with some consequences sometimes. We say that the antecedent is sufficient to achieve the consequence which is necessary. So I can call the thing on the left the statement that's sufficient, the sufficient statement. And the statement on the right is going to be the necessary statement. Once the left side has happened, it's sufficient, it's enough, it's finished, and that means the thing on the right side is necessarily going to happen. If P is true, then that means Q on the right has to be necessarily true as well. Sometimes we say that P implies Q. On Blackboard, you'll find under the list of textbook examples for this section, I've also listed some of the tables in this section as examples that you don't quite work through as an example, but I want you to read through. That helps with some of this language. P implies Q for the conditional statement. Here's an example. If you get a raw score of 90% or higher, then you will earn an A in this class. I seem to have misspelled then. The logic way to write this in symbols is a symbolic format for this is P implies Q. My statement P is you get a raw score of 90% plus, and my statement Q is you will earn an A in this class. Notice something else about the logic of this. It doesn't follow that if you've earned an A in the class, then you must have gotten a raw score of 90% or higher. There's other ways to earn an A. For example, in my class, if you have an 89.5, in fact, if you have an 89.49, I'll round that up to an 89.5, which I'll then round up to an 90%. So you can get an A without getting a 90% or higher. It's possible. You can be as much as 0.51 of a percent lower than a 90%. You still get an A. So it doesn't go both ways. If then is very specific. There's a precise antecedent, and that leads to a consequence. And just because the consequence happened doesn't mean the antecedent happened. Again, going back to that bow and arrow idea, sure, I could shoot an arrow out of a bow, but I could also probably go and poke something with my arrow, and there didn't need to be a bow involved in the process. The consequence would be the same. It's just my antecedent's been messed with a bit. So you'll have a very specific left implies right. It's a very precise direction. If you do have something that gets to go back and forth, that's what we call the biconditional. In English, we would talk about this as if and only if, and the arrow is going in both directions on this left side here. In math, we say if and only if so often that we abbreviate it IFF. So if you see an IFF, it's not a typo, it means if and only if. Again, this is called the biconditional. Biconditional statements go both ways because they're bi. Yeah, I just said that. So if the United States is attacked with significant civilian casualties, then we will go to war. That is a statement. I might call if the United States is attacked with significant casualties, statement P, and we will go to war as statement Q. If I can also assert that if we are going to war, then we were attacked, this gets me this sort of joint statement. If and only if the U.S. is attacked will we go to war. I kind of think this is mostly true. Again, I'm not trying to get involved in the politics of the situation. I kind of feel like maybe Vietnam might be a little iffy, but I'm thinking, like September 11th, we were attacked, and so then we've gone to war, regardless of your opinions on that. I'm also thinking maybe a World War I and II. Probably World War II mostly. I don't know about the British when we got our independence, but I'm sure they wanted to attack us. So if we and only if the U.S. is attacked will we go to war. Maybe that's a nice statement to make. The idea is you can go in both directions. If I'm able to enter my office, then I'm able to exit. If I have exited my office, that means I must have entered it. So I can say I'm able to enter my office if and only if I'm able to exit it. And that might be another biconditional. It's hard to get into biconditional things, I think, because it requires a much greater burden of proof. So your book gives you some examples. There's lots of examples in math with theorems, which from our previous discussion, a theorem is something that's always true. But it's a little nasty to get involved with. For all of these also, again, I've got the tables put on Blackboard under the textbook examples, but I also, again, page 117, page 119, table 3.8, 3.9. These help you understand and get going with what's going on with this. So now let's get into this philosophy behind logic. The idea is we're trying to get rid of fluff, emotions. We need to get rid of the unneeded modifiers. It's basically the opposite of what every English teacher ever wanted you to do. You don't just get to talk about, okay, there was a forest around a mountain. No, it has to be a forest filled with ancient trees, creeping up to the foothills of the majestic purple mountains that tower over us into the awesome sky or something. We want to get rid of all those fluffy adjectives. So the first thing you do is replace every statement with the letter P, Q, R, S, or T. One of those letters usually we seem to use. Then you replace all the connecting stuff with these logical connectors. There's two ways we can do this. You can either turn an English statement into a logic statement, or you can turn logic statements back into English. So I want you to remember your order of operations in math. because it said PEMDAS, parentheses, exponents, multiplication, division, addition, and subtraction. And what PEMDAS really let us do is make sure that when you and I look at 3 times 4 equals plus 2, that we both get 12 plus 2, which gives me 14 out of this, because multiplication is more important than the addition. So I first do 3 times 4 and it gives me 12, then I add the 2 and get 14. If we didn't have this agreement about what the order of importance was, then maybe you'd first do the addition and give me 6, and then do 6 times 3 and give me 18. And that's not what we want. That's wrong. That's incorrect there. So we mostly have this order of operation to make sure that you and I, when we write things in symbolic form, have an agreement. So here's the symbols we've discussed so far. We have negation, we've got conjunction, we've got disjunction, we've got conditional, and we have biconditional. And then just like in math statements, you do things inside the parens first. So here's some statements that I've got. I took them from a song by a pop artist. Statement P, my heart is broken. Statement Q, I can cut you into pieces. And statement R, I can't yell any louder. So let's look at what these things mean. If I have this not on the outside and then inside the parentheses I have P and Q, then what I do here is I first look at the inside part. Statement P is my heart is broken. I have and, so I have and then Q is I can cut you into pieces. And the not at the front, this not here, is the part that gets tacked on and says, it is not true that. So then I have this statement, it is not true that my heart is broken and I can cut you into pieces. The whole part that I've got highlighted here is the part that's not true, which means, incidentally, for our logic, and you'll see this when we get more into section 3.3 and later, maybe my heart's broken, maybe I can cut you into pieces, but I can't do both together. If my heart's broken, maybe I'm too depressed to go cutting people into pieces. Okay, so that's where this not true part comes in. Again, here is my biconditional going on, so I know I'm going to have if and only if in the middle connecting everything. And then on either side of it, I've got not P and not R. So R is the statement my heart is broken, which means not P is going to be my heart is not broken. R says I can't yell any louder. That means not R is I can't not yell any louder, which means in English we don't do double negatives. That means I say I can yell louder. Yeah. So I have my heart is not broken if and only if I can yell louder. That means if I'm yelling louder, that means if there's no louder that I can go, I'm yelling as loud as I can, my heart's clearly intact and fully angry. If my heart is broken, it's not broken on the other hand, then I probably can go yelling louder. That's what this if and only if means. And lastly, again, another one of these not statements in the front, which means I'm going to have this, it is not true that. And then inside my parentheses, I have P for my heart is broken. I've got my if and only if statement. And then I got my R, I can't yell any louder. So it is not true that my heart is broken if and only if I can't yell any louder. If I can be yelling louder, my heart's not broken. If my heart is broken, I'm probably too depressed to be yelling too loud. So, got these directions of these statements here. That is pretty much section 3.2. Again, I want you to go onto Blackboard and go into the textbook examples and work through the examples and make sure you thumb through and think about each of the lines and rows in the tables that I've suggested you look at to get a good feel for this. This is the foundational stuff that we're going to build up the rest of chapter 3 on to make this logic